All right, on this video, we're going to talk about another use for uh, a line integral. Last video, if you watched, we talked about circulation, which was defined to be the integral of f dotted with t ds. You may recall that was the more sort of theoretical formula but to actually calculate circulation, we use either this formula f dotted with dr, or this one where if we define f to be a vector field made up of m for x and n for y, and r is a position function that defines a curve xy, it would be the line integral of n dx plus n dy. And remember what we're finding, what circulation measures, this brings it out more. If you think about it traveling along a curve, the tangent vector at any point sort of gives you the path of that curve right at that point. And if f is a vector field, when we do the dot product, what we're actually measuring is how much of that field is acting in coordination and in the same direction as our tangent vector. And that could be interpreted as if a particle was on this curve and this was a force field, it could measure how much that force field is pushing that particle along the curve. And that led to that discussion about circulation and work are actually the same integral, because that's the definition of work, is a force moving a particle, a mass, a certain distance. So anyhow, that was circulation. Another idea here that we'll talk about is the idea of flux. And flux is measuring how much of f acts perpendicular to a curve, not tangent, but perpendicular. And we can interpret this. So here's our picture. If I've got a curve here and f is acting at some angle, what I want to measure now is how much of f is acting perpendicular to the curve. So now I want to do the dot product of f and its normal vector. This is called the outward unit normal. So that's our definition for flux. And you could sort of think of this, we talk about simple closed curves. For flux, we want to think about an area enclosed by a curve. Simple just means it's not going to be something that like crosses over itself like an infinity sign. And closed means that obviously it has to loop back around. There can't be any openings. So if you talked about a simple closed curve, what flux could be measuring is, if you can imagine a vector field, this one sort of looks like something emanating from inside the curve and spilling outward. It's measuring how much of the vector field is crossing the boundary. How much is, if you think of it as a fluid, which is another common analogy for a vector field, it's how much fluid is crossing this boundary. So how do we calculate this? Well, okay, some definitions then. If flux comes out to be positive, then if we use the analogy of fluid again, what that means is more fluid is leaving that area. That's positive. It's going across the boundary outward, away from the closed curve. If we get a negative flux, that would mean more fluid, or some other parameter that f might be standing for is flowing into C rather than outward. So you can kind of imagine, I mean, the field I drew here, obviously it looks like everything's leaving, there's nothing coming in. But you could imagine a vector field like this crossing over a boundary where, yes, you do have some stuff coming in, some fluid coming in. But the way I tried to draw this here, notice that the arrows here are shorter, would indicate a smaller flow inward, whereas as it's leaving, it's a much greater flow. So this one, I would still probably, if I just looked at it, predict that I would get a positive flux because I have more stuff coming out than coming in. Okay, so let's go back. One of the examples on the previous video that we talked about for circulation is we took a unit circle here defined by cosine t sine t. That is a closed simple curve. And we did talk about this vector field xy. That's a vector field that for any given point is going to produce a vector that's just moving purely away. And those vectors are going to get bigger as X and Y get bigger. So you have like smaller vectors here, then they get bigger going this way. So this vector field is a radial field. It's all your vectors are pointing purely away from the origin. And when we use this one, when we talked about circulation, we did a circulation calculation for this one, and we found out that the circulation, not surprisingly, was 0. And that's because, again, a circulation, if you interpret it as, how much of any of these vectors is serving to push a particle along the curve, it's not. It's pushing directly against it. It's trying to push it outward. And that's why the circulation came out to be 0. But in terms of flux, that's actually what we're measuring. We're measuring how much of this field is pushing outwards across the curve. So you can imagine this is going to have a very, probably the most positive value for flux we could get for any field, because every vector is crossing this purely perpendicularly. One thing of note when we get to our definition of flux is that this particular vector function, cosine t sine t, does trace out a circle counterclockwise. If you start at 0, you're going to be at the point 1, 0. And as t increases, just like going around the unit circle in trig, we're going counterclockwise here. There are other parameterizations we've talked about that can produce a circle as well, but maybe tracing it clockwise, or starting at a different point other than 0, 0. There's lots of ways to parameterize a circle, but this parameterization will start at 1, 0, trace it out counterclockwise. Now, how that becomes important is we've talked about the definition of flux. It's the line integral of f dotted with n, where n is the unit normal outward vector, ds. And similar to the circulation formula, put that back up here for a second. We had sort of 3 definitions for it. This one was sort of the more theoretical definition, in that we don't often actually find T and ds. ds is a unit of arc length, which you might remember is a kind of a complicated thing. We had easier versions of that. Same thing for flux. This is the more theoretical definition, but how do we actually make this more accessible, easier to calculate? So to do that, we're going to look at this curve, this same circle we had. I tried to draw it 3D here. So imagine it's in the XY plane. Remember, the way we parameterized our curve is it was starting on the positive x-axis and it was being traced out counterclockwise. So that's why I have the arrows going this way. If we then imagine a point on this, here's our unit tangent vector. Here's our unit normal vector that's pointing outward. That's what we want. We want to find a way to calculate that. And k hat is, recall, that's just the unit vector pointing straight up in the z direction. And making that little angle there, recall that if I do a cross product, I produce a vector that's perpendicular to both. I'm going to do a cross product with either k crossed with t or t crossed with k. And recall the order that I do that cross product, it gives me a vector perpendicular to both t and k. But the order matters. One will produce a vector pointing inward, and the other one will produce a vector pointing outward. I want the one that's pointing outward. And it was all governed by the right-hand rule. You remember that one. If I put my right hand on t, and pull it into k, hopefully you can see that would produce a vector pointing outward. If I did it k cross t, that would give me a vector pointing inward. So the order I want to get an outward unit vector is t crossed with k. So let's actually work that out. Remember, to do a cross product, I'm going to have I, j, k. T, this is in the xy plane. So remember, t would just be, the tangent vector would just be dx and dy. It's how much you move in the x and the y direction. So for t, we'll put that here, dx, dy. There is no z component to t. We're in the xy plane. And k is 0, 0, 1. And remember your cross product. We're going to block out the first row and column. And we're going to do the determinant of what's left over, which is dy times 1 minus 0. So I just get dy. For the middle, now I'm going to go to the middle column, block out that row. That automatically gets a negative. And if I block out the column and row for that one, I get just dx minus 0. So I'm going to get negative dx. And if I do the k component, I'm going to get 0. And really, I just want this, it's going to be in the xy plane anyhow. So I'm just going to have dy negative dx is my n vector. And so what that means, to come up with a better formula, if I once again define f to be mn for my x component, y component of my vector field, f dotted with n ds is going to be f mn dotted with, this is n, it is dy negative dx. And if you do the dot product, we're just multiplying and adding. The formula that we'll use most frequently to calculate flux for now, flux across a curve is going to be m dy plus n times negative dx, but we'll just put that negative in the beginning. So it's m dy minus n dx. This is the formula we'll use for flux in the plane. So back to our problem. For the circle we were talking about that had the radial field xy, my flux is m dy minus n dx. X would be cosine t, right? Remember x, if my field is x, x is cosine t, right? So my field is really, well, this is going to be an integral from 0 to 2 pi, because remember, that's how we traced out that curve. M is x, but x is really cosine t. dy is right here. Dy would be cosine t as well. Minus n. N is y, but y is sine t. Dx, well, there's x right there. Dx is negative sine t. dt. And this gives me cosine is cosine squared t. Negative makes that plus sine squared t dt. And of course, that's 1. And the antiderivative of that is t from 2 pi to 0 is going to give me a flux of 2 pi. Again, remember for that particular radial field, the circulation is nothing because you're not pushing anything, but the flux is actually 2 pi. That's a positive answer, means that more vectors are flowing out of that circle. In fact, all of them are in that particular picture. That's why we're getting a positive answer. Now, if we contrast that with, let's do the same circle. I just want you to highlight the differences between flux and circulation. Same circle here, but this time we'll use the field negative yx, which, if you recall, that was producing a spin field. If you take points around the circle and do negative yx for your vector, you're going to get vectors that look like this. That is a great field to have if you want to have a big circulation, because it's going to definitely push things around that circle here. But if we're measuring flux, which is, again, all these vectors are coming, these are just the ones on the perimeter, right? There's the same similar vectors inside. They're just going to be smaller, right? So you have vectors going like this. But all throughout here, flux is supposed to be measuring how much of these vectors are pushing across the surface. Well, they're always tangent to the surface, right? There's no, at a microscopic level, these things are right tangent to the circle. There's nothing that's pushing anything across the boundary. So intuitively, I expect the flux of this field across this boundary to be 0. So let's just confirm that. This is my M, this is my N. flux. It's going to be a line integral, this parameterization from 0 to 2 pi, that's x, that's y, m dy minus n dx. My m is negative y, but y is sine, so that's negative sine t. dy is derivative of sine t is cosine t, minus n, which is x, which is cosine t, dx, which is negative sine t. Notice I get negative sine t, cosine t, minus minus makes that plus. So this whole thing just comes out to be 0. And so as expected, the flux is 0. All right. So in order to do flux, we need to have a closed boundary, a closed curve, simple closed curve. Circles are very nice, they're closed curves, but can we calculate the flux amount around another closed curve? In this case, we're going to do the flux. We've got a different field here. Outward across, this is a triangle joining these 3 points. So we should be able to calculate the flux. I have no idea what this field looks like, but we're going to measure how much of this field is pushing across the boundary. So this one gets challenging because the only way to do this is this triangle has 3 sides, unlike the circle where we could just use one parameterization for the boundary. We have to separately do 3 separate parameterizations, straight line parameterizations between these 3 points. The other thing to keep in mind is the way flux is defined, we're measuring, tracing this curve counterclockwise, right? Curve expressed or defined counterclockwise. I say that because, there's ways of parameterizing this line segment going from here to here, but we want to go from here to here. So kind of going back to the, how do we parameterize things? For curve 1 here, we want to pretend a particle is right here when t is 0, and it's right here when t is 1. So in that 1 unit of time, x goes from 1 to 0. So it started at 1, and every unit of time it's losing 1. So that's why it's 1 minus t. Whereas y goes from 0 to 1 in that 1 unit of time. So it's just going to be 0 plus t, or just t, from 0 to 1. R2, again, now you'd kind of, to parameterize that, let's pretend a particle's here when t is 0, and it's winding up here when t is 1. Same idea. How does x change in that 1 unit of time? Well, it goes from 0 to negative 1. So it's just going to be negative t. And for y, it goes from 1 to 0. So it started at 1, and it's losing 1 unit every unit of time. So that's 1 minus t. All these parameterizations will just be from 0 to 1. And then, for the final one, same idea. Now you cross this out, pretend we have a particle here from t equals 0, and it winds up here when t is 1. And starting position is negative 1, but in 1 unit of time, notice x gained by 2, so that's why it's going to be negative 1 plus 2t. Whereas y is just always 0. So you've got to do those 3 parameterizations, and then one by one, we need to compute the flux. So on R1, my field again is up here. It's x plus y minus x squared plus y squared quantity. So what I'm doing here on R1, which is right here, this is x plus y, and this is negative x squared plus y squared. And I'm just putting in, right, this is x, this is y for R1. I'm putting those in for x and y. And if you simplify that, you get, this is just 1 for x for m, and this is what n simplifies to. So our line integral is going to be m dy minus n dx from 0 to 1, because that was our parameterization. So for m, it's going to be 1 times dy, which is dt, minus n. Okay, dy, there it is. Yeah, dy was dt, right? It's right here. The dy is dt minus n, this is n, dx, because the derivative of 1 minus t is negative 1 dt. So what we could do here to simplify this, I stopped my calculation here. So this negative, if I apply it to this one here, is going to make that plus. So I'm going to end up with 1 plus negative 1 plus 2t minus 2t squared. Looks like the ones cancel out. And if you integrate that, that's going to give you t squared minus 2t cubed over 3 from 1 to 0. Gives me 1 minus 2/3 minus 0. So I'm getting an answer. I wrote down the answer, make sure I got the right answer. I'm getting 1/3 for this. And then you have to do the same thing for the second parameterization. This was the left side of my triangle right here. That was my r of t, so that's my x and y. My f field is m. This would be my m, x plus y, so I'm just adding those together. And then negative x squared plus y squared, if you simplify that, gives you this. So I'm going to have m 1 minus 2t dy is the derivative of this, so that would be negative 1 dt minus n times dx. Dx here is also negative 1, basically negative 1 dt. All right, let's see if I can not mess this up. So if I distribute this negative 1, I'm going to end up with negative 1 plus 2t. This negative 1 combined with this one will make that plus, and then I can just add those. Negative 1 plus 2t minus 2t squared. This time they don't cancel out, so I end up with the integral negative 1 and negative 1 is negative 2 plus 4t minus 2t squared, negative 2t plus 2t squared minus 2t cubed over 3. Whoop, from 1 to 0, not from 0 to 0. So I'm going to get negative 2 plus 2 minus 2/3. And of course, if I plug in 0, I get nothing. So I get negative 2/3 is my answer there. Final one. On R3, this was our parameterization. F simplifies to this. Check it yourself. And so if I do the same thing, how about this? I'll leave this blank. Make sure you get that answer of positive 2/3. Make sure you can do that integral. And it boils down to this then, the total flux across the triangle. I have to add up all three of those, the fluxes across each boundary. Flux 1 plus flux 2 plus flux 3. The last two ended up canceling out. So my total flux across this triangular boundary is 1/3. So you can see the complexity. If your curve, your closed curve has to be defined by multiple line segments or multiple curves, it becomes tedious because you have to calculate the flux separately across each boundary. So circles are much, much better. All right, thanks for watching.